Hello, my name is Matthew Landis, and this is my Lab 1 presentation on constant velocity. This lab explores the constant motion experienced by an object, meaning that the speed and direction are unchanging. It includes a real-world demonstration of Newton's second law of motion, as the net force is zero, so the velocity is constant. The law is also known as the momentum principle and says that if an object is not experiencing any net forces, then its motion will not change. Labs like this, that are focused on the fundamental physics principles, helps not only continue to verify the legitimacy of these laws, but also help to act as a point of connection between the physics theories to their true-to-life counterparts. To demonstrate this phenomenon of unchanging motion, I have recorded the physical movement of an object without applying any force, and then coded a simulation that would model the same motion digitally. After executing the experiment, I found that the computer model was able to closely predict the position at any given time. The data collection for this lab began with the recording of a constant non-zero motion of an object, in this case, slip bomb. Afterwards, I uploaded the video into Tracker and set the coordinates, the scale, and placed the center of mass point. I then took this data, graphed it, and extracted the necessary data to complete the code, which I will explain more in a later slide. The most important value that I solved for was the average velocity over the time interval t equals 0 seconds to t equals 1/4 seconds. This was done by dividing the change in position by delta t. With the plotted data from both the physical object and the simulation, I was able to make some observations. I saw that the physical object slowed down over time, which is likely the result of frictional forces, which were not included in the model. However, besides this discrepancy, the physical object followed the predicted motion quite nicely. Seen here is my completed glow script code written in VPython. The most important modifications that I made to the original code was that I input the velocity, which remains constant throughout. I also changed the delta t value, which made the code output the same number of data points as the tracker software, which helped when combining the data sets into a single graph. Some smaller changes I made came in the form of creating a secondary graph for the velocity and changing the position update formula, which actually takes into account the albeit unchanging velocity of the ball at any moment, rather than the pre-coded vector. This code assumes that there are no net forces acting upon the object in motion, and uses the position and velocity update formulas to move the object, both of which are derived from Newton's second law of motion. On screen now is a screenshot of the completed simulation. The simulated object moves at a constant rightward velocity, which closely resembles the motion seen earlier on the slide before real-world testing. Beneath the first and second graphs, showing the object's position versus time and velocity versus time respectively, there's a print window that allowed me to export the motion data and visualize it in a combined graph with both the simulated and observed motion. The completed link will be included at the end. Improved slides for improvements. The observed and simulated motions did not perfectly match each other, as shown in the combined position versus time graph. This discrepancy is likely the result of having imperfect test conditions. To have perfectly constant motion, all forces must be balanced, resulting in net force of 0. However, the observed object was actually experiencing friction forces while in motion. The test could be more accurately representative of constant motion if testing was done in a vacuum with a surface with lower friction coefficient, which would reduce air resistance and contact friction respectively. The model could also be changed to take these forces into account. However, this would no longer be simulating constant motion, as there would be unbalanced forces. Here are some of my final thoughts regarding the execution of this experiment. When analyzing the video of observed motion in the tracker software, if I were to have flipped the orientation of the axis, this would only have changed the velocity to a negative vector of equal magnitude and given a downward sloping position and versus time curve. The same analysis could have been done regarding the motion. Additionally, although we could see that there were nearly no forces acting on a real-world object, we can never know the number of forces that are acting on this object to give this result. This is because there's no difference in the motion of an object, whether they have no forces acting on them or if they have two or more equal forces acting in opposite directions. The only thing we can know for certain is that if there is a zero net force, then there cannot be only one force, because there must be some unknown number of other forces that exist to balance out this force. Thank you.